A modern shale pad is an exercise in massive scale. You're pumping millions of gallons of fluid and sand at extreme pressures, and every minute of pumping time directly impacts your return on investment. Downhole, the mechanical objective is straightforward. You have to force proppant, heavy sand, deep into subterranean rock fissures, wedging them open so hydrocarbons can flow back to the surface. But water alone cannot suspend that much heavy sand. It drops out. To carry the proppant, you need to radically alter the fluid's viscosity. You need a chemical thickener. The industry's default is standard Guar Gum. Look at this surface-to-wellbore fluid transfer diagram. Standard guar from surface tankers thickens water to carry sand downhole, but downhole speed is chained to the surface. You must mix and store the powder in massive holding tanks. The chemical viscosifier you choose dictates your surface footprint, your continuous pumping capability, and ultimately the financial viability of the entire pad. The flaw with standard organic guar gum is its hydration curve. To reach its functional viscosity, standard guar powder needs up to 2 full hours to absorb water and uncoil its polymer chains. A 2-hour delay means you cannot mix and pump simultaneously. You rely on a sprawling footprint of batch mixing tanks to let the gel mature, creating a bottleneck. An idle wellhead bleeds capital. Waiting on fluid hydration inflates the operations cost by the hour. To eliminate that wait time, operators are turning to fast-hydrating guar gum, specifically grades like BD Guar's Hydrocolloids FHGG. The proposition is compelling on the surface, but to evaluate if it actually improves your bottom line, we have to see if accelerating the surface mixing compromises the extreme thermal stability required downhole. FHGG achieves its speed through physical and chemical engineering. The raw guar split is processed to a significantly finer particle size and chemically treated to disperse instantly in water without clumping. This chart graphs the resulting hydration curves. The standard guar takes a slow 2-hour climb to reach peak thickness. The FHGG line spikes almost vertically, achieving a functional pumping viscosity in just 3 minutes. Looking at the manufacturer specifications for ICOL FHGG, the fan viscosity results confirm this. At exactly 3 minutes, the fluid hits between 28 and 40 centipoise. Over the next 60 minutes, it gains another 5 to 6 centipoise as the chains fully hydrate. Getting rid of the batch tanks requires a shift in infrastructure. To run a 3-minute hydration cycle, you must move to an on-the-fly continuous mixing model. That means investing in specialized high-shear blending equipment at the surface to ensure the powder disperses evenly. However, trading static holding tanks for high-shear blenders allows for continuous, non-stop pumping. Maximizing active injection time directly lowers your final cost per barrel. Surface logistics are only half the equation. Once the fluid enters the wellbore, it hits a high-pressure, high-temperature environment, where the rock can exceed 150 degrees Celsius. At those temperatures, a linear guar gel, even a fast-hydrating one, will quickly lose its viscosity, thinning out to the consistency of water and dropping the proppant entirely. To survive the heat, introduce a cross-linking agent. Metal ions lock loose guar strands into a rigid, viscous network to carry sand. Borate is commonly used. A table shows it creates reversible bonds, recovering from mechanical shear and reforming when fluid slows. The trade-off with borate is strict environmental control. It only maintains those bonds if you perfectly balance the fluid's pH between 9 and 11. For hotter wells, operators often pivot to zirconate crosslinkers. Zirconate bonds can withstand significantly more thermal stress than borate. But zirconate forms covalent, permanent bonds. If pump friction rips them apart, they do not recover, and you lose proppant suspension. A fast-hydrating guar is useless if it fails under pressure. Keeping the sand suspended requires an expertly managed chemical architecture perfectly tailored to the well's specific temperature profile. Once the sand is successfully wedged into the rock fissures, the thick cross-linked gel becomes a liability. It has to be removed so the hydrocarbons can flow. You inject breakers, targeted enzymes or oxidizers, designed for chopping the rigid polymer chains back into a thin, watery liquid that can be pumped out. This exposes the inherent risk of using an organic material like guar. If the breaker chemistry fails to degrade the polymer completely, insoluble residue is left behind in the well. This chart graphs viscosity reduction against organic damage. When unbroken guar residue permanently clogs the microscopic pores of the rock, it throttles the flow of oil. You avoid this formation damage by pushing the fluid into this optimal top right quadrant. Hitting that target requires incredibly precise dosing of your breaker chemicals, calibrated exactly to the bottom hole temperature. A fracturing fluid's performance depends as much on its complete removal as its ability to transport sand. BD Guar's FHGG is a highly engineered operational shortcut. It solves a massive logistical problem at the surface, but it still behaves like an organic polymer downhole. You slash your hydration time from hours to minutes, making non-stop continuous pumping operations possible on the pad. That speed demands execution. You must implement flawless surface blending, maintain strict pH control, and deploy precise breaker chemistry to prevent formation damage. The logistical premium you pay to source a fast-hydrating guar is only justified if your site crew possesses the chemical expertise to manage its life cycle perfectly underground. This makes FHGG the ideal solution for operations managers running high-volume, multi-stage fracturing pads in moderate to high-temperature wells, specifically up to 150 or 160 degrees Celsius. Under those standard conditions, pairing FHGG with a borate crosslinker provides the most efficient chemical and logistical profile for optimizing cost per barrel. But there is a hard thermal limit. If you are drilling ultra HPHTW wells consistently above 175 degrees Celsius, standard organic polymers will fail. At those extreme temperatures, you have to accept the significantly higher financial cost of using fully synthetic viscoelastic surfactants or heavily modified derivatives like CMHPG. For the vast majority of modern shale operations, BD Guar's high-call FHGG masters the delicate balance. It gives you maximum surface speed without sacrificing reliable downhole strength.